First, thanks to the organizers. It's a fantastic meeting. It's a great place, of course. All right, so SPDEs, you all know. RSDEs is something I will tell you about today. Maybe some people have heard bits and pieces of this before. This is, of course, one paper that's in the archive, but this is also somehow a bit of program, at least for me. My co-workers here are Coale, who is now leads, Antoine Hocquet, who is still in Berlin, and here two younger people. I'll tell later what they're doing. All right, so let me start with motivation. Since it's an SPDE meeting, I will start with SPDEs. And so there's one that's particularly famous. It's the Zakai equation. So it's a SPDE for a measure-valued process. So if you hit it with test functions, then this is how it looks like. Of course, you can write it out using the adjoint and in a standard weak analytic form. And what is L here? That's the second order operator, might be degenerate. So here is, we sum over repeated indices. And this guy here is a first order operator that also has a transport term in it. So the interesting case in filtering is, at least for some people, that you have really this term here that corresponds to a correlation in the setting. And here, we make these structural assumptions that this diffusion, this matrix here, has this form here. And if all this is in place, then it's classical that you can write the solution of this SPDE, here it is, which is really, it's SPDE, so it's random. You can write it using this conditional expectation where you, utilize a system of diffusions. I mean, in a sense, I'm turning it upside down because the problem starts with this process here, which has the interpretation of a signal, and then you try to figure out what you know about the law of the signal given your observation, and then you come here to the Zakai equation, but I'm telling you it the other way around. So I suspect this will be familiar to many people in the room here. Let me just point out that the system of diffusions, also known as stochastic characteristics, they're naturally driven by two patches of Brownian motions. Here is the W, the Brownian motion that you see in the SPD, and there's another one that somehow is tied up to the, to this diffusive operator here. Right. Also important, you have this exponential term in here that comes from this Kessanov change of measure that is behind the scene, and I'm talking too slowly. So I prepared a one slide, why interesting, but I don't really want to spend much time on it. So just in a nutshell, the W you have in the Zakai equation corresponds to the observation process that is under the, let's say, original measure. It's a Brownian motion with a drift, and the drift somehow is, has access to the signal process here. And then you do a change of measure that turns this guy here into a genuine Brownian motion under a new measure Q. And it's really that under this new measure Q that you have this elegant representation here, that this the original problem here, the filtering, so you want to access the law of the signal given the observation under the original measure here, that you can tweak it around and have this so-called Bayes or Kalyan-Stribel formula, where these guys here are given by exactly the expression we had on the previous page. So here you can tell this as a standalone story without filtering. And but if you put it in this natural filtering context, then here this would really be the measure that you get after this change of measure. It's the Q measure here. Okay. So all I'm telling you is that this is an interesting SPD, and there's a natural particle or diffusion SDE system attached to it. Here's a second example, a stochastic HGB, Hamilton-Jacobi-Bellman equation, that was suggested in this form by Lions-Sougandis 25 plus years ago under the name stochastic viscosity solutions. And to be fair, they were not interested. I mean, they give this as an example, but they were not really interested in the case where this noise is linear, but they had examples where this is nonlinear, which is, of course, much harder. Even so, this was proposed back then. And so this bit here, so let's look at it in a bit more detail. You have here second order operators that depend on some eta and some control space. Then you do the usual, soup procedure. Then you get a fully nonlinear second order operator. This bit here is the HGB equation as a backward problem. Let's say you have terminal data. and then you have this extra. So if you forget this for a moment, this is a classical problem, and you have here that this PDE, this backward PDE, is is the PDE satisfied by the value or by the cost function that you have when you do stochastic control of Markovian diffusions. So if you put this extra noise term in here, then at least formally, if you pretend this is a frozen, C1 path, this is why we like Stratonovich, because it, suggests the correct calculus, then formally you might say, okay, well, it looks like the guy I should be looking at is this controlled diffusion here, where this transport term here lurks around as some drift here that I do not wish to control. So, otherwise you quickly get trivial and boring, non-interesting results. If you look a bit closer, so first remark is, this is random now. So you have to be careful what you mean by taking soups. So I should have put an omega here. I should do this. I should paint it red, but let me not do this. So you should be careful with soup. So we take the essential soup. That's fine. And then the next thought you have is, okay, what is actually the class of admissible controls here? So of course you must not look in the future, but what is the future here? So since you condition on this whole noise here, your controls should be allowed to make use of. I mean, this is also a critique of this model here, because the controls inevitably will look at the future of, the entire path W. So if you like it or not, it's not our problem in a sense. We're interested in these SPDEs. But the subtlety here is that if you work with such extended admissible controls that are also allowed to look here, that are not only adapted to the filtration of B, but also to the filtration generated by B and the full information FWT, then you quickly get into some anticipating things here. If you put this in here, it's not a classical, so it's subtle. And many people worked on this. I should mention Bogdan, Ma, but maybe I come later to this. All right. So the take-home message of this example is, here's an interesting nonlinear SPDE, and again, there's some process in the back that has somehow two batches of Brown motion, one of which we condition. Now, since I'm interested in financial mathematics, here's a recent example from finance that I'm quite happy with. So postmodern is not official terminology, but somehow, maybe for this slide, it's okay. So the problem is to do option pricing. That means you want to compute the expectation of some payoff function, which I call psi here, of some suitable process. Let's assume it's a martingale. Let's think in a second. So if you can't wait to see what it is, it's maybe something like this. So if you have any interest in finance, or you have been, supervised master theses on Heston models and stuff, you can think of here, this might be, without this leverage function L here, this could be the Heston model, but I'm very general about this volatility process. All I'm saying is adapted to this red filtration, the one generated by W. And so again, this fits many, basically all classical stochastic volatility models. And there's a recent, fancification of these, that you put this extra term here. It's called leverage function. And these are known as local stochastic volatility models, and they're extremely popular in the industry for reasons that I don't want to explain in detail, but you feel free to catch me over coffee. So this is not some academic exercise. These things are used in practice very much. So what you can do here is you can, you can actually do option pricing in such models here by solving some intermediate SPDEs and then average over a certain martingale noise. If this is a good idea or not, this is it's also up for debate. There's some reasons why this is a good idea. There's some other reasons why this may not be what you do on a trading desk. But here we go. So it's basically that the remark is that the model as I've written here may be highly non-Markovian, and recent developments like rough volatility suggest that this. Also a reminder when I'm too slow. There's no a priori assumption that this is can be extended to some finite dimensional Markovian system. This may be very much non-Markovian. And yet, it's conditionally Markovian. So formally, if you freeze everything what I painted in red here, what you see is something that's Markovian. So there should be a PDE, a backward PDE. So what would look like? Well, if you, so now I should, go back up. So stick with me for a minute and just let's look at this backward PDE. So there's the usual diffusion operator here, sigma square. So look at this evolution here. The sigma is the coefficient for the B. And once I freeze the red noise, this becomes deterministic. And here I have this other bit. So this here is the diffusive part of this here. This has to do with E to Stratonovich because here we have E to and here we have Stratonovich, so don't worry too much about it. And then we have this transport noise, which I want to write in Stratonovich form here. So if you buy that this SPDE here has a good meaning, then it's it's reasonably easy to convince yourself that you have somehow a Feynman-Cast type representation of solutions, which is just given by the usual here's the payoff. You start at time ty somewhere here, and everything is conditional on the red one. So you're in PDE setting again. It's conditionally Markov. So there's a PDE. Now, I have checked with a few people in the room over the last year, this martingale noise SPD as it stands is actually, I don't know a good way to make sense out of this SPD as it stands without rough paths. So you can, if you're a classical SPD expert, maybe you can challenge me on this one. The problem is that you solve it backwards. So if you do any sort of integral formulation of this one, let's say with test functions or otherwise, then you would need to, you have to go backwards. But a martingale in the forward filtration is not a martingale or semi-martingale when you go backwards. So the integral meaning of such terms would be a bit awkward. Anyway, if you're happy to think in terms of rough paths, and here it's even a scalar setting, so there's no problem whatsoever to turn this martingale here into rough paths. You just attach somehow the 1/2 square of the increment. Then this fits in nicely into existing ideas. So, right, I should say a little bit more. This actually ties up with a classical trick in finance, and maybe at least one person in the room will, maybe two, will know about this. Romano Tussi, in a famous paper from '96, made the remark that in stochastic volatility models where you don't have this leverage function, if you condition on the red stuff, what you have is Gaussian. I mean, it's sort of, in hindsight, it's all obvious, but it was a nice remark at the time, and still is. And so that means when you do, when you look at this conditional process now, look at the Fokker-Planck equation, I mean, you have a Gaussian structure here. So you can actually, in this case here, write down the solution to this SPD, whatever the SPD itself may mean, but you actually know what it means because you can write down the solution quite explicitly. Okay, so this is like for fixed time t, so we come from time t backwards to time 0 here, you can just get the solution here by integrating up. So here's a Gauss measure, normal law. Here's the mean that depends on the realization of this stochastic integral. And here's it's okay. I hope I got all the rows and 1 minus rows right, but it looks okay. So this is the Romano-Tussi trick in somehow this rough PDE language. That contribution here, if you want from a finance perspective, is that we can go away from this Gaussian setting and deal with general Markovian things, which is nice. So now I've given you 3 examples, and I could have given you a few more whenever you have, let's say, particle systems with common noise, and you have a propagation of chaos, and then you get some mean field SD, but then you also have this common noise around. So there are more examples where you have this structure here. You have 2 batches of noise, Brownian noise, B and W, or maybe martingale noise, B and W. And what you want is to understand this guy conditionally on the second Brownian motion. And at least for me, the obvious thing to do is to try to make this a rough path, which is an analytic object. And then you can do everything you want. And later in the day, you can randomize this rough path. So you plug in basically Brownian motion and iterated integrals. and then you recover, the original problem. And why is it useful? Because you have a great understanding of this one. You can work with a conditional object. This is, in general, not the same in martingales. All the classical calculus fails, but here you have a very elegant view. So particularly you get somehow, if you're interested in the regular conditional distribution of this, given all the information of your red Brown motion, then this is exactly the right thing to do. So the rest of the talk is, I've shown you that many SPDEs somehow come with underlying systems of this form here. I will talk about RSDEs, tell you how it works, and then we go back to these SPDEs and see what's in for the SPD people. So first, a few recall on rough paths, and since time is ticking, I don't want to spend too much time, but a little one I have to. So let's keep it simple. Everything's multidimensional, but our notation is not. So here's a rough differential equation. What does it mean? That X is basically something like, think of a Brownian motion and its iterated integrals, and then you formalize a little bit what these objects look like. So the alpha Hölder, the second increments also have some Hölder regularity or Hölder type regularity. And then there's some algebraic behavior of these iterated integrals, how, this is so-called chain relation. And a very direct, short way to say what this means is just to say, well, you have somehow a Milstein type expansion here. So if you do stochastic numerics, this is the Euler scheme, this is the Milstein scheme. And then you just define this remainder term J by imposing this identity here. And Davies said, well, if this remainder here is small here, then you call it a solution. That's a definition, and then you can go ahead and prove existence uniqueness for nice enough data. Of course, F, you're not in the Ito world, so you need a little bit more. F is C1 over alpha, or think C3 to cover this regime here. When there's a condition on alpha when you want to prove this, and here it is, alpha should be between a third and a half. All right, so Davies is elegant, but it's not the most elegant to prove things. It's quick to explain, but if you want to, how to get your solutions, you try to run a fixed point argument like in ODEs. And this is goes back to Massimiliano Gubinelli. Of course, Terry Lyons had, worked this out previously, but in a much more complicated way. So Massimiliano had the, I think, most elegant view. And so he says we work in a space of controlled rough paths. These are paths that locally look like the driving signal X here, and this is captured by this modulation function. And then again, you make a higher order remainder ansatz here and also impose a little bit regularity on this one. So in a very precise sense, it generalizes what people have done for many years when they look at, Lipschitz functions for, lib2 or lib3. This is very much the same spirit, and then Martin has formalized this, in a grand way with model distributions. So it's similar ideas. The good thing about these spaces is they're stable under composition with regular functions. So in a sense, there's a push forward given by, in this natural way, and it's the good space of integrands. Namely, if you think of an integral formulation of this, at some point you have to integrate something. So if you call it f of y or y, it doesn't matter because, after pushing it forward, it's another y. Or okay, for this reason I called it z here. And so what is it? What should it be? Well, it's left point, and then we put in the, like Milstein's spirit, we put in this extra helping friend to get analytic convergence, provided you have, the good regularity here. And then the lemma that does this for you, this is a statement. This is the limit exists as your mesh of the partitions goes to 0, mesh size. That's the Sewing lemma that does it for you. And once you have it, you can again plug in Brownian motion. So Ito Brownian motion, you take a Brownian motion, attach the iterated integrals. This is now the so-called Brownian or Ito Brownian rough path, and you go back to the SDE. What did you gain? You factorize the Ito map. The Ito map takes noise to the diffusion path, and we have factorized it. So we go first from W to this W rough path, and from there we go analytically to Y using this machinery, and this second arrow corresponds to continuous map, and here's the metric where you have continuity. So of course, in stochastic analysis, this is a big deal because then many things fall out quite easily, like support, large deviations, Wong Zakai, etc., etc., etc. If you haven't seen the Sewing lemma, it's some abstract Riemann integration. So what you're trying to do is you sum up little things and hope for the best. And if these things happen to be additive already, So they are, you know, let's say they are somehow AT minus AS, then the sum here is trivial, it telescopes and you're done, right? And so this condition here tells you to what extent you fail to be additive. And if you don't fail too badly to be additive in this analytic sense, then you can imagine that the summation, you know, as you sum up with some geometric, you know, series will work. So this is in a nutshell, this is the Soing lemma. Back to our problem, how do we go from here to here? To get you a bit of perspective, I mean, these ideas, you know, the need for such a theory has been around for a long time because I showed you all these examples, so it's very natural. One thing you can do is a flow transformation. You say, okay, well, I don't really understand this one, but I understand this equation, and I also understand it on the level of flows. So it introduces a flow of diffeomorphism, and then you just play around that you make the ansatz. Okay, I say this y here, formally pretend this is smooth. I just say, you know, let me work out the equation for y tilde that I've written in the new coordinates that are adapted to this noise. And if you do this, then you get this equation here. That's a good Ito equation that you can solve. So you never made sense of this equation here, but you made a transform which is robust. So all these you know, the ways you perturb these coefficients here depend on your x. And if you control the flow here, if you know that your flow of diffeomorphism is robust in the rough path matrix, then of course you can pass a limit here and check all the continuity properties you want here. But again, this way you get this stability, but you never somehow really understood what this equation means. So this is somehow the list here, no intrinsic definition. So if you had different approximation, let's say discrete, then this flow transformation would be a big pain. You need nice flow of diffeomorphisms. If you have jumps, that's also not good. The bad regularity demands for F, because to get a nice flow here, I mean, here you have to play around amongst others with Ito and then get some control. So you need more regularity on this vector field than you would in rough paths. So in rough paths, the rule of the thumb is you have F should be 1 over alpha, or you can think C3, and here you would basically need C5 or something. And it's just a very rigid method. It works, but you know, you pay a price, several prices, in fact. There's a different method that was proposed by Joscha Diehl, Harald Oberhauser, Sebastian Riedl. Say, okay, well, let's not follow Ito. I mean, here we pushed it back to the Ito world. Let's push it back to the Lions world and think of the whole thing as a big rough differential equation. What is the driving rough path? Well, it's somehow the pair of a good old Brownian motion, which I think of here as a sample pathwise, and the trace of the rough path x here. So you can make this work provided you can lift this pair here to a proper rough path. What do we need? We need the second iterate integrals. Well, for x, that's easy because x already came as a rough path, so the second iterate integrals, they are already in your hand. For b, you have a Brownian motion, so no problem. You just fire up Ito and do all these integrations. And for this one here, you just define it by integration by parts, which is not a harmless assumption because somehow you say you believe that there's some independence going on. And if later in the day you randomize with x, which is correlated to b, then your calculus will not be consistent. So if you keep that in mind, and you can do that, then you solve it somehow omega-wise as a random RDE, and it works. You can check that the map from x here into this space of random rough paths has the right continuity properties. But again, you pay on the Lions side. So for instance, the sigma, which is in the Ito world, should be Lipschitz. Here suddenly needs to be something like C3. So, and the other problem is there's absolutely no way that in this rough setting here you could make sense of sigma with somehow progressive dependence. So when you want to do stochastic control, this is a no-go. Right. So here's the real thing. How much time do I have left? 15. Okay. Okay. Should be good. So how's the real thing? Well, yes, somehow you have to go back to the origins and do everything correctly bottom up. So we need the right space to work in, and this is a space of stochastic controlled rough paths. And the reason people didn't, do this, I mean, we wrote the first paper on this 10, 15 years ago, almost, okay, 10. Why didn't we do it back then? There was a tool missing. The tool came in the form of stochastic sewing. That's Hocquet proposal. I'll show you what it is. If you haven't seen it, I think it's very powerful. I mean, everyone thinks that. So I'll show you that in a detail, but the upshot of this is that we have, I believe that the good, I mean, I'm pretty convinced that the good theory of these rough SDEs, so everything now comes in the natural regularity class, the Ito data is Lipschitz, the rough data is 1 over alpha as it should be. Also C dot means also controlled. It means I can also allow F to be time dependent, even with rough dependencies, if I put somehow some F prime, some Gubinelli derivative in, but let's not fuss about this. We can put sigma here, we allow for the full progressive generality as you need in stochastic control. And also there's still enough somehow martingality left in the setup. So if you go back to the Lions setup, where you do everything omega-wise, you've given up completely on any martingale knowledge. I mean, it's painful to recover it later in the day when you need it. But here it's somehow, you haven't given up on that. So the martingale structure is still there. And so let me show you the stochastic sawing. I've shown you the sawing before. So the new thing here is, in the sawing, there was only one condition, there was no expectation, and there was only this 1 plus epsilon that told you that these guys are somehow almost additive. And now this is significantly weakened, so we work in some moment spaces. I'll comment on this in a second, but take m equals n for a moment, and then this is just the moment space of exponent m. And so what I'm saying here is that this, the 1 plus epsilon that we had in the sawing earlier now got significantly reduced to 1/2 plus epsilon. It's a world of difference. On the other hand, you have this 1 plus epsilon here only, or you need it only up in parachuting some conditional expectation. And this, of course, will kill all martingale increments that are around. So this will add a great deal of cancellation to the problem. And so these are the two assumptions. And now it's a lemma that there exists a unique stochastic process, which is, there's some adaptedness conditions around. So this is a 2-parameter stochastic process. Adapted means that it's for every fixed ST, it's FT measurable. And on all these assumptions, you basically get a stochastic process, calligraphic A, that is somehow well approximated, or the increments of that process are well approximated by these ingredients that you started with in this conditional form estimate. And again, there are 2 estimates that somehow mimic this one, but now with the limiting process that you constructed. So why do we need this? Well, the simple answer is if you try for a proper integral formulation of this, if y at the end of the day is an adapted process, then this is harmless. This is an Ito integral, no problem. But this integral here needs understanding. And for this one, we need stochastic sawing. So we can't use sawing because y is not controlled by x. There's this b around, but the stochastic sawing will somehow kill this martingale bit, and then you're in business. So in a nutshell, this integral dx relies on this stochastic sawing. And why do we bother with this mixed moment norms? It's a bit weird. So if you take m equals 1 and n equals infinity, this is actually related to BMO processes. So they're not totally, weird, and they have been used in homogenization in the 80s, I think, in a paper by Varadan. But I have not seen them previously in, let's say, in our little world. But they will be absolutely crucial, and I will explain to you why. There's also a sketch of this one. Okay, let me spend just a minute on it. So if you take m and n equals 2 for simplicity, and also let me simplify life by taking this one 0. So I wanted this conditional, differences here is actually 0, which happens, in fact, if you do simple Ito integrals of the form f of b db. So this is, I'm not talking about the empty set here. And in that case, it becomes particularly clean and sweet. So you do this, how do you get the limit? Well, it's the same dyadic idea as before. You sum up these little things. And so if you look at the difference between 2, dyadic levels here, this precisely makes appear these what I call delta AI here, which has, this is a shorthand notation for such differences here. And the assumptions we have exactly guarantee that these guys here or these are martingale increments. So you have a discrete martingale with energy identities. And so, boom, here you go. You have a nice estimate in L2. We can just, there's no contribution off diagonal. You put in your assumption here. So I'm using now this one here. Up. Again, if m equals n, this just collapses here. And you have you're doing this in L2. And then you see that this 1/2 plus epsilon, it comes with another factor 2. So here you're at 1 plus 2 epsilon. And that's good enough to get this convergence here. And so, of course, there are a lot of details when you write it down in this general case, but this is the essence of it. So how do we make sense? So I should give you a definition. The easy to explain one is, again, Devi. So you write down, so this is formal. We don't know yet what this means. But as I pointed out, the first two guys has no need to do anything because we're looking for some adapted process. We have progressive coefficients. So this, let's just keep them as E2. There's no need to expand anything. But here, of course, we do need to do something. And so you do the usual thing. Here's Euler, and here is Milstein. The F here is the df, d little ff. So this is the Milstein. I also put in F prime. This is somehow this control structure that I can also put in. We need in some applications, but let me not worry about it. And then this defines me a remainder. And this is, of course, stochastic now. And this is not negligible as it was previously in the sense that you have an exponent greater than 1. Here we just have 2 alpha. Alpha is less than 1/2, so this is not true. But if you think which terms you're dropping here, they would involve somehow these martingale bits and somehow cross integrals of this b and x here. And so, you know, these guys are not little o of t minus s. So this messes up this, you know, this analytic negligibility we had previously, the Davy definition. But if you change it to some, you know, if you put a conditional expectation here, then it's actually true, or you make it a definition, but you can, you know, do some back of the envelope computations to see why this should be so. And so this is the condition. Instead of, you know, old style Davy, where you say there's remainder is a little o of t minus s, you say the remainder upon taking conditional expectation is a little o of t minus s. And then you have a proper, well, okay, this is not a precise definition, but this is the idea. And under this, if you make this more precise, then this gives you a definition, and we can prove after a long day that you have a unique RSDE solution. I will show a bit more here. So as before, the Davy view is not the ideal view to prove it. It's quick to explain. So to prove it, we need a good space where we can run the PK iteration. And this is the controlled or stochastic controlled rough bar space. So let's be guided by some formal expansions here. So if I am, you know, the remainder in sort of in this Gubinelli language here, in the SRDE setting or this setting here, you look at the increment of the solution, you subtract somehow this Euler bit, and then what you're left with is, well, is still this Ito bit. So that's not small. That's on a scale comparable to this one. And then you have higher order terms. So in particular, the classical analytic condition that the remainder should be of 2 alpha, this is what you do in, you know, classical controlled rough bar theory, is not working here because this guy messes it up. But all you have to do is drop this conditional expectation that will nicely kill this thing here, provided sigma is not crazy. So this is really a martingale increment. And then you have your good estimate with the 2 alpha. So this gets a name. We say that Y, or this is an example of a process that is stochastically controlled in the sense that this conditional remainder is small or higher order. All right. So how do you go off? Now you say, okay, we have understood. So we can put all these guys into the right norms, put the Banach structure, then you just, you know, prove that you have invariance of some ball and contraction, and it's all done. It's almost not quite. So let me review the strategy for RDEs. The PCAR map, let's ignore silly things like adding, you know, initial data or something. The PCAR map is essentially a composition of, first you put something in a regular function, you have this composition, and then you integrate, right? And then if there's a fixed point to such a thing, to this PCAR map, that's a solution. And in RDEs, and also actually in single SPDEs, Martin can correct me if necessary, you can do all this basically with one norm or norm-induced distance on a space of controlled rough bars or model distributions. It's not quite true. You have to tweak a little bit the Hölder exponents to make some power t to the epsilon appear so that you get your invariance and your contraction, make things small. This gives you the small, the local well-postedness, okay? There's some obstacles here. So, you wouldn't voluntarily start to work with these mixed moment spaces. So if you just say, okay, let's do an L2 theory or LM, then you run into the immediate problem that these stochastic controlled rough bus on this LM scale are not stable under composition. This is very annoying. So there's no way you can close any loop. You lose and lose and lose. So you have to be a bit smarter and understand this composition here in this mixed moment scale. And then you understand that the loss that occurs is broken up. So it's broken up that only one of these two, I can't go into great detail here, I'm sorry. Only one of these two exponents here is actually affected by this composition, and generically, you lose a half, okay? So fortunately, we can just take n equals plus infinity, which has the property that, infinity half is still infinity. So that fortunately works. So it's a little, if you think of this BM op space as one infinity, so that you have that the second one as infinity is, it covers still, we're still in the good class here. What you certainly do not want to do is take both of them infinity, because then you're, in a space that doesn't even contain Brown motion. There's a second obstacle, namely when you do the contraction. So this is a problem you have to deal with when you want to prove invariance of some closed set. The second obstacle is that the local Lipschitz estimate you need when you do the composition. So for the contraction, you need some local Lipschitz estimate, that this does not hold in this LM infinity scale. It's somehow too strong. So that one you only get in LM. So now you have these two guys to two different matrix rows. And so the good news is that you can work with both somehow at the same time, and that the ball, or actually it's some weighted ball, some ellipsoid, that you define using this DM infinity norm that you inherit from LM infinity, is still a complete metric space under this weaker distance. So this is something I'm sure PDE people, nonlinear PDE people use all the time, that they have some invariance in H1, and then they prove convergence in L2, but the limit necessarily, because bounded set in H1 is still in H1. So in nonlinear PDE theory, I'm sure people, so I'm told people have used this or used this frequently, but in our context here, I've not seen it before, so here we go. And then, at the end of the day, here's a theorem. Under the natural assumptions, you have a unique L2 infinity solution, so also LM infinity for any m less than infinity. Depends a little bit how much randomness you want to put into your vector fields, which can also be stochastic. But if you take them deterministic, then this is true. And so if you have two of these guys and you compare them, then you have, so these are somehow what you see here is at least part of the norm that we put on the stochastic controlled rough path spaces. And then you have a complete, you have local Lipschitz estimates in the complete data. So in B, sigma, F, I'm not telling you what this means, just think of a F being in C3, and so this would be some lib3 distance between the vector fields. And here is of course, these two together are the rough path distance. Here's the dependence on the initial data, which is also allowed to be random. Okay, so I don't have much time left, but we should go back to the applications. So remember what we wanted was this guy here. This was the Zakai SPDE told you something about this thing here, and then we had this particle, or this diffusion representation here. And so here it is, actually, I wrote it back out for you. So what you do is simply, instead of messing around with these conditional objects, you do it on the level of RSDEs, very pretty. Then you can do this here. There's no conditional expectation whatsoever. All you have to do is, at the end of the day, you randomize, black W is now rough path, and then you randomize it, make it a random rough path, the one associated to this Brown motion W. What's the benefit? That this thing here is immediately robust in rough path metrics, which was the main result of an old paper of mine with Grisan and others. But this derivation is much, preferable, I think, and also the assumptions on the coefficients are, significantly dropped. So this is useful. And let me point out one more technicality here. Right, it's this thing here. We need exponential estimates for this here. There's one thing to define it as limit in LM. It's another one to get exponential estimates. So the good news is that all these stochastic controlled rough paths are actually elements in some quantified BMO or vanishing VMO actually space, and therefore you get the exponential estimates essentially for free. Okay, using some non-trivial ideas of other people, but this goes back to Varadan and others. And Hocquet recently wrote a paper where he revisited all this in a quantitative way. In some previous archive version, we had a pedestrian argument, but so it's really the right thing to do is to embed it into this BMO language. Then we have the pathwise stochastic control problem. So, whatever this SPDE really means, that I'm happy to discuss over coffee, the value function that we wrote down here, as we indicated, if you do it properly with another noise part here, then this essential supremum here is a bit fishy, what does it really mean, and anticipating SDs, etc. All these problems evaporate in a second when you switch to a rough path here, right? It's a proper supremum, there are no conditional expectations, there's no anticipation, so this is immediately well defined. And moreover, you can get very easily, so again, in some sense, this satisfies a solution to a nonlinear rough partial differential equation. And you can just from this stochastic representation here, you can deduce, because we know everything about y. We have full Lipschitz dependence on the data, so we can just extract from these estimates that are shown in the theorem, you can extract a bunch of estimates for these value functions. If you compare it with different rough paths, different points in space-time, different terminal data, so all this you get out for free. That's answers actually a question that was raised back then by Buktan Ma. I did not want that. What else can you do quickly? Dynamic programming. So I'm not sure when you taught last time such things in classroom. It's not, if you want to be honest, it's not trivial. But here we can just, take a smooth ride. You use the results that you know. So you have the Bellman principle here in the smooth case, no problem. Everything is robust in X. You immediately go to rough path limit and you're done. Two-line proof. And last but not least, this is implicit here. If you ask yourself in this HGB equation, okay, so if X is smooth here, right? Then there's no question that this value function is the viscosity solution to the usual HGB equation. And so this is what I mean here with the epsilon. And the estimates we had tell you that these HGB equations here are actually robust here in the rough path sense. So this is also a result we did with analytic methods and flow transformation with Oberhauser many, many years ago. But now this somehow gives you a direct proof with the stochastic picture behind the scenes. So much improved regulated assumptions compared to these flow transformation methods. And then I'm probably out of time, am I? Rough PDEs, this is very quick. So you can use these RSD representations also to prove intrinsic well-postedness of these rough PDEs. The keyword is forward-backward duality, and so existence, the one gives you uniqueness for the other, and so you can get uniqueness with these representations. And this also works in a mean field setting, which is works by Kogan and others. So there's much more to come. I have not talked at all about mean field, but this is, and here's Outlook references. Thank you very much.